All right, guys, welcome to Statistics 5.3. We're going to be talking about um, binomial distributions again here. So we're going to talk first about how we can graph them. So our procedure for when we graph these, we get all of our different R's, which are going to be our number of successes here. And those are going to be just like, so like 0, 1, 2, 3, 4, 5, up to however many successes we can have. Right, then in a similar way to how we made a histogram, since we need these values to actually have width, right? Because 1 doesn't have width, but if I go from 0.5 to 1.5, now that does have width. So I'll actually see a physical bar there. So what we do is we extend every R value half a unit lower, half a unit higher, and then that gives us our width for each bar, and then the height is going to be the probability of that particular outcome happening. So it ends up looking a bit like a histogram, and we kind of use it in a very, very similar way, which is why we try and make it look like one of those. So here we have a situation that we're going to be looking at. Jim makes about 50% of his field goals when playing basketball. Now, for those of you who think that's a football term, you're an idiot. Well, no, you are wrong. A field goal in basketball is a standard 2-point shot. That's what it is called, in case you didn't know. So, anywho, so if I'm looking at what is the so he makes about half of those in his game. So let's go ahead and pause, work through A, B, C, and D, see what you could do, and then come back here and we'll go through them. All right. So the first part here, we have 6 different trials, and a success is making a like shot, and that's going to be a 0.5 chance, right? So then, if we fill out our table here, right, in the same way as we've kind of done in the past year, to get 3 right, that's 0.5 times 0.5 times 0.5 times 0.5 times 0.5 times 0.5. But then we gotta look at, well, how many ways can we get that? So if you use that process, which we had last time, of 6 combination 3 times 0.5 raised to the third times 0.5 raised to the third, then we get that 0.312 and so forth for the 2, the 5, and the 6 there, right? So it's the same process as we did last time in 5.2 to get those numbers there. Then, so that tells us our different heights. We then make our widths, and we get a histogram that looks like this, right? So this one's very symmetric and pretty right there, around that middle value of 3. Now that's only really happening because it's 50-50. If it's 50-50, you're always going to get that nice, perfectly symmetrical graph, right? If I make it 60-40, it'll still have that mound shape, but it won't be perfectly symmetric anymore. And that also has on D, that is why your probability of getting 4 shots is the same as getting 2 shots, is because it's perfectly 50-50, right? All right. So how can we compute the mu and the standard deviations here? So mu is super easy for us to compute. It's also called the expected number of successes, which is something you probably would have intuitively done if I had have asked you on that last slide. If he makes half of his shots and he's going to take 6 shots, how many shots do you expect him to make? Well, you say, well, half of 6 is 3, so he's probably going to make 3 shots. That's what this is, right? You would expect him to, and his average number of shots made would be that 6 times 0.5, or in this case, 3, right? Then to calculate the standard deviation, this is a little bit, again, of an ambiguous thing as to kind of where it comes from. I'm not going to define it for you because it's really, standard deviations are a lot harder to define where they come from. It just takes a whole lot of time and work. But this is a pretty easy one for us to actually use and plug things into, right? It's the n, which is the sample size, times the probability of success, times the probability of failure, and then again, we always square root it because that's where standard deviations come from. So go ahead, pause, answer problems A and B there on the bottom half, then we'll go forward here. Right, so again, we already kind of did A, to 6 times 0.5, because that's your probability of success. And then for my standard deviation, 6 times 0.5 times 0.5, because success and failure are both 0.5. And then we square root it, and you should get about 1.22 as your standard deviation there. All right, so let's take a look at this in a different context. So this is a bit of a longer one, so I have broken up into multiple slides here. So the overall situation here is that a satellite needs to be powered by at least 3 solar cells. The probability of one of these cells failing is a 0.15, and we assume that one cell failing does not affect the probability of any other cells failing, which is why we say, hey, it's independent. All right, so part 1. We want to find the least number of cells that a satellite should have so that the expected value of the number of working cells is no smaller than 3. Okay, so we need 3 or more cells working is fine, because once we have less than 3, our satellite no longer has the power that it needs, so it can't function properly. Right. So in this situation, N represents the number of cells, R is the number of successful or working cells, and P is the probability that the cells will work, Q is the probability that the cell will fail, and mu is the expected value, which should be no smaller than 3. So first, so they're going to kind of walk us through here. So go ahead, pause, work through A, B, and C, and then I'll come back and we'll go through them. All right, so what's the value of P and Q? Well, P is going to be 0.85, because there's a 0.15 chance of a fail, so a success is going to be 0.85. Right? And then our Q is our chance of a fail, which they already told us is 0.15. So expected value of mu for the number of working cells is given by mu equals n times v, which we already went over, right? So the expected value of the number of working cells should be no smaller than 3. So we need 3 to be less than or equal to n times p. Okay. So if we do that, our p, which is our probability of a success of 0.85, we get 3.53 as our is less than n. So our number of cells has to be greater than or equal to 3.53, right? So since this is between 3.3 and 4, right? Well, we say, then do we need 3 cells or 4 cells, right? I'm always going to round up here, right? Because so thinking about the context of the case, right? It says, hey, I need 3.5 cells in order to expect 3 of them to work, right? But I can't send half of a cell. So should I send 3 or should I send 4, right? Well, if I send 3, that's going to lower my expected value to under 3, because I'm going to be rounding down there. So we always try and be more safe. So we're going to round up to 4 and say, well, 4 will provide more a mu of greater than 3, which is 3.4, which is higher than we need, but it's better than being under what we need, which is what 3 would end up giving us. All right, let's take a look at the second part of this, right? So we want to find the smallest number of cells that the satellite should have to be 97% sure that there will be adequate power. Because even though the expected value is 3, that's great, but there's still a decent chance that if I only send 4 cells, it could not work. So A, B, and C are going to walk you through this process. So go ahead, pause A again, and come back and I'll walk us through it. Okay, so the first thing we're trying to do here is figure out, well, what terminology are we trying to say, right? We need our R's, which is our number of successes. Do we need that to be bigger than or equal to 3? or less than or equal to 3? Well, we need our successes to be 3 or more, right? Having 5 working cells is good. It doesn't cause problems, but only having 2 working cells is very, very bad because now my satellite can't function. So I want to use the the probability of R being greater than or equal to 3, being 0.97. So to do this, right, we need to find the value of n such that P of R is greater than or equal to 3 is equal to 0.97. So if we say, let's make n 4, right? Well, then that means that either R is 3 or R is 4, because my number of successes to be greater than 3 is either 3 or 4 if my sample size is 4. So I need to find my probability of 3 successes plus my probability of 4 successes. So to do that, right, that same formula we've been using for a bit here, right, I would say, well, my probability of, it's going to be, I have 4 combination 3, and then that times, I want successes are 0.85 times, I need 3 successes and 0.15 time to the 1 power for that 1 fail. Okay. And then so it's that, or I could get 4, choose 4 where I have all 4 work, times 0.85 raised to the 4 times 0.15 raised to the 0. Right? So if I go and I do both of those, and go 4 probability 3 times 0.85 to the third times 0.15 to the first, I get that. And then if I do 4C4, which is always 1, times 0.85 to the fourth, then anything raised to these zeros is always 1 as well. I get that. So then that plus my 0.368475, I get 0.8904, right? Which is a good chance, but that's not at that 97% that I need. So I'm going to have to have more than 4 cells. So let's try 5 cells, right? For 5 cells, I have 5C3 times 0.85 to the third times 0.15 to the second now, because I need 2 failures in this case. This is, there we go. There, okay. So then I also need 5, choose 4. So what if I have 4 work out of those 5? That's 0.85 raised to the fourth times 0.15 to the first. And my last case is I could have all 5 of those 5 work, which is going to be 0.85 to the 5th power, 0.15 to the 0. So let's see if this is enough for us here. So 5 combination 3 times 0.85 to the third times 0.15 to the second. I get that. And then 5 combination 4 times 0.85 to the fourth. Oops. To the fourth times 0.15 to the first power is just 0.15. So I get that. So I want really this plus this. So I have 0.52. Then the last thing that I have to add is this, which is 1, and this is 1, so it's really just 0.85 raised to the 5th power. Let's do this. Plus 0.85 raised to the 5th power. And I get 97.3, right? Which is higher than my 97%, success rate that I'm looking for. So what that tells me is back over here that, well, having 4 wouldn't work, right? But having 5 would, because having 5 takes my probability of having at least 3 work to being higher than 97%. Now, if I'm sending a satellite into space, I probably want a higher than 97% chance that it's going to work, because that costs millions upon millions of dollars just to send it up there. So that's why we'd probably want higher than that, but for the sake of an in-class trial, we're only going to stop at 97% for hopefully obvious reasons. So again, not terribly hard what we just did there. It's a little bit tedious because you have to kind of keep doing the same little bit over and over again, but your calculator can do all of that for you, so it shouldn't be all that big of a deal. All right, with that is it for 5.3. Oops. Where's my cursor? There we go. So there is our homework for 5.3, doing 1 through 2, and then also 3 through 27 odd. With that, I will talk to you guys next time.